Hello friends, today we are going to talk about nonparametric statistics. I slightly introduced what is the nonparametric statistics. We just want to review them again today. Most of the statistical inference procedures we have discussed up to this point are classified as parametric statistics. The concept of parameter does exist in population distribution. So examples of parametric statistical tests, z-test, t-test, f-test. Since these tests are working for parameters related to parameter estimation, so we call it parametric statistics. The most common uses of this test are for this testing hypothesis about the single population mean or the difference between two population means. These are all dealing with the parameters. One of the assumptions underlying the valid use of this test is that sampled population or populations are at least approximately normally distributed. The procedure is not concerned with population parameters or not depending on the sampled population is non-parametric. What if we cannot define any population distribution? So we have no way to talk about the population distribution. In that case, we don't think about the population distribution. That is actually non-parametric statistics. Also, it says distribution-free procedures. There is many advantages for using non-parametric statistics. First, they allow for testing of hypotheses that are not statements about population parameter values. Second, non-parametric tests may be used when the form of population distribution is unknown. 3. Non-parametric procedures tend to be computationally easier and more quickly applied than parametric procedures. Consequently, 4. Non-parametric procedures may be applied when the data being analyzed consist merely of just rankings or classification. So we don't use the individual data itself. We transform into the rank. Okay, which one is smaller, which is larger, something like that. We're talking about the ranks or classifications. So also there is a big disadvantages. So they should be recognized. The use of non-parametric procedures with data that can be handled with the parametric procedures results in a waste of data. Okay, so whenever we know what is the distribution of this data, then we better go for parametric procedure, not non-parametric procedures. Actually, in that case, we will have a result by non-parametric procedures is a lower efficiency compared to the parametric procedures. The second, the application of some of the non-parametric tests may be laborious for large samples. For small samples, it is very easy and quickly, but it becomes a large where we don't know anything about the population distribution. Then we have to go to the non-parametric procedure. Is kind of laborious. Okay, you have lots of things to think about. So the unique feature, when I say unique features non-parametric method, is they do not need specific algebraic values. Okay, we need only rank. The most cases they are converted into order statistic. Order is equal to the rank. In many cases, each non-parametric method has its own tables. It's very complicated. Okay, we have to look for the many tables to get the outcome, the hypothesis testing for this non-parametric method. In clinical studies where we cannot specify its own distribution, non-parametric method are preferred. Also, in clinical studies, we cannot use many cases to look at. So in that case, since the sample size is very small, then sometimes the non-parametric method is more useful, particularly when the sample size is small, so that its distribution may not be determined. because sample size is so small, so we cannot draw any kind of distribution. So we cannot determine any kind of distribution. Then we can use non-parametric method useful. Okay, there is actually there's two families: parametric method family, non-parametric method family. So in parametric method of the family has all different hierarchies. For example, when we have one sample, we can conduct a t-test or a g-test. Also, when we have two samples, then we can also conduct the t-test or g-test for the comparison. Also, the paired comparison, okay, they are another t-test, okay. Then for this one, there's another the non-parametric test equivalent to this test. So sign test and sign test with not paired data, and the Wilcoxon signed rank test for location, and median test and mean-Whitney test. All these tests are for the compatible with this t-test or g-test. Okay? And also when we try to know whether population data is normal or not, so there is a method for testing for normality. Okay, the same thing, we have a Kolmogorov-Smirnov goodness of fit test. Okay, there is a kind of same thing to check for the normality. So in chi-square test, we learned about how to check for the normality by using chi-square test. The same thing. And also when you move to the ANOVA test, more than 3 cases, okay, so it's one-way ANOVA, the two-way ANOVA, then we have equivalent test for the non-parametric test. The Kruskal-Wallis one-way analysis variance by rank is compatible with one analysis variance. And second, Friedman two-way analysis variance by rank is compatible with blocked design in two-way analysis variance. So this is not ANIVA, now ANOVA. Then Pearson correlation coefficient is compatible with the Spearman rank correlation coefficient. So all the matching, the methods are there, parametric versus non-parametric method. The first thing is for sign test. Sign test, where as we saw this one before last week, so we have with 10 girls here. So everybody has some scores about the mentally retarded 10 girls. Okay, they got the score like that out of 10. Then suppose the mean values as a 10 is maximum value, and suppose 5 is median value, then it's maybe populated, but maybe the score may skew to the upward or skew to the downward. Okay, it could be, but it is desirable because median is 5, so the rate is scattered around the median value. So the high hypothesis population median is 5, and the check for whether population median is not. So that's the null hypothesis and alternative hypothesis. So test statistic, actually, based on this one, we have to look at the upper value compared to the median or lower value compared to the median. So number of upper value, lower value is equal. Then we may say the median is 5. Okay. In that case, according to this logic, we can develop 3 alternative hypotheses like that. Okay, then what is the distribution of test statistic? Test statistic, so is actually before we look at the distribution test statistic, is here. So we have table. So compared to the median y, the median value is 5. So compare the 5 value. If the value is lower than 5, it will have minus value. It's higher than 5, then it will positive value. When they equal to 5, then it's going to be 0, like here. Then, so the probability of having positive and probability of negative is equal to 5, equal. So 0.5. That is actually the null hypothesis. Okay, based on this one, with decision rule. Okay, according to alternative hypothesis, when positive probability and negative probability can be seen this way. Okay, three different way. Okay, here as you see here, so all three different alternative hypotheses. This first two, this one and this one is actually one-sided test, and last one is a two-sided test. Okay, so since we have only positive and negative value, so in that case, test sets follow the binomial distribution. Do you remember that one? So in that case, we have only one. The negative value here. So having the such situation is we can develop use a binomial distribution probability density function. So when this one is x, right? Xk, k is here. K could be 0, k could be 1. At most we have one minus sign. So we have to cover the probability on the one. So we have to calculate this one and this one. So when we calculate this one is 0.01195 and this one is 0.01758. So altogether probability is 0.0195. Okay, so this probability is very low. We actually the previous calculation is done by hand. But another way is when looking the binomial distribution table, then we can get this probability, okay, according to this situation, okay. Then as a total sample size n, as the p is 0.5, then k is number of minus sign, okay, up to 1. So there's extreme probability, okay. Then conclusion, you conclude median score is not 5. Okay, so there's a significant the probability very low compared to our probability alpha. So we can say that we can say that we have to reject the null hypothesis. Okay, then the p-value for this test is one side the probabilities they did this one, so we have on both sides two-tail test, so we multiply 2, so altogether only probability is less than 5%. Okay, that's the sign test. This is the output from a computer Minitab program. So here we have then the below case that we have 10 cases here. Below 1, equal 1, above 8. Okay, so when you calculate the probability, 0.0391. Okay, so in real from this data, real median is 6.5, not 5. Okay. And second one is signed test. It's kind of very similar to the t-test with paired comparison. Okay, is here we have two people making one group. Okay, the pair number is that. So the one people two for each pair is two people. Okay, for one pair among each pair, one person in each pair is instructed something, and then score is not instructed something. There's two group of people. So this one has instructed, it is not instructed. Okay, so about the oral hygiene instruction, then after a certain period of time they check the result, so whether there is any difference between instructed non-instructed within a pair. Pair is actually looks like a block pair, right? Paired design is very similar. Okay, so that's the sign test for paired test. Let's look at how the process is going on. So here we check the number. So we do not interested in what is the difference between two values. Only thing is when we the instructed group minus not instructed group. So we are looking at the calculate difference. The difference is our main interest is whether which one is larger and lower. Okay, so the instructed is higher. This one is this is x minus y. So instructed people has score is minus. It means not instructed people score is higher. It means lower is value is better. Okay, then minus positive 0 is an equal value. The minus, and for the number 4 is the rather instructed cases higher value than the non-instructed value. The same thing is happening in 11. So we have 1 0 and 2 positive. Okay, then this actually is the same thing with the sign test at this moment. Okay, that the only thing is we have we group each pair with the 2 cases, not one. So it is a pairs. That's the difference between sign test. Okay, so actually when we come up with this table, so we have to think about the same thing with the by sign test, the same thing. And calculation of the test statistics according to binomial distribution table, then we say it is significant or not. Okay, so we have to take out the 0 cases. We have to eliminate them. Then case reduced to the 11. Okay, so it was the 11, 2 pluses and 9 minuses. Okay, so based on this one, we calculate using binomial distribution here, as you see here. Binomial, you can calculate them. The probability is 0.0327 is still less than 0.05. So we have to reject null hypothesis. Okay. In this case, the p-value is the calculated value itself is the p-value. Okay, next one is Wilcox assigned rank test for location. This data is a little bit different from previous one. We have here how many? 15 patient data. This is all the cardiac output data. So these patients went through some cardiac surgery session, and after this cardiac surgery session, they measured the cardiac output. Okay, so the 15 patients showed this data. It's a 491, 4419. Okay, individual data is expressed in numerical style. Okay, then our question is whether this mean value is 5.05. Okay, so the question is whether each individual value is maybe a little bit away from the 5.05, but I just want to know whether this value is around the mean value or not close to the mean mean value or far away from the mean value. I just wanted to check them. Okay, so here in this case also we need some assumption. The sample we have sample here. Sample is a random sample. Okay, all the variables measured in continuous scale, and the population is symmetrically distributed around this mean mu. What it means is we have mean value here. Then in order to have a mean value like that, half of the cases may be under mu. Okay, the other half may be over mu. Okay, then this mu has a meaning. Okay, in that case we can say symmetrically on both sides, up, above and lower, something like that. So that's the case, and the measurement scale is at least the interval. Okay, so we develop hypothesis. This one is a user two-tail test. Okay, so we set up the mu values here on whether my original the population mu is equal to mu 0 or not. Okay, this one is alternate. It is according to the situation of the data. Is if we prefer mu should be lower than the null hypothesis value, then this one's mu is higher than null hypothesis value. So it depends on situation. You can pick up any kind of hypothesis. Okay, here, then we have the data here. Okay, data is listed here as it appeared in the exercise, the previous the slide, as that is not ordered in magnitude. Okay, so first one is first, the last one last. Okay, then based on this one, we calculate the DI. What is the DI? DI is the deviation from individual value, deviation from mean value here. So xi is at 9.1. 9.1 minus 5.05 is minus 0.14. And for the second one, 4.19 for this one is minus 5.05 is minus 0.95. In this way, we calculate every deviations here. Then based on this data, we are looking at the only absolute value, not minus. Forget for a while, forget about the minus sign and plus sign. So it's looking at the absolute value. Based on absolute value, we put the rank. Okay, the lowest one is 1. Lowest one value is 1. The highest value is 15. And this one is done according to the magnitude of the DI value. Okay, we put the individual rank here. Then in this column, we get the minus sign again here. So we have the minus sign like this. Then in the rank, we put the minus sign. That the result is like that. The same way, all the other ranks will have the same the signs, minus or positive. We have seen this as we seen in this column. Okay, this one. Then we have a rank here, 15 ranks here, and some positive, some negative. So we add all the positive values. Okay, positive ranks, and T positive is 86. And this one is when we have how many minus 1, 2, 3, 4, 5. 5 minus is we rank is 34. Okay, so we have to divide two type of rank sum. If we adding all the ranks here, then it would be 120. Okay, 120. So when you add this one plus this one, it's going to 120. But this one, this rank, 120 rank is divided into two according to their the signs, minus or positive, something like that. Okay. Then here, in this case, we pick up smaller value. Okay, t is equal to 35, 34. Then I will explain it why we pick up smaller one. Okay, this is the procedure. Di equals I minus B0. If Di is 0, then eliminate it. Okay, the same as I did before. The sample size will be reduced accordingly. And then the other case is if the three values has the same numeric value. Okay, we cannot put which one is higher and which one is lower because they have same value. For example, for the rank, for the three values, lowest, there is a three lowest value. Then they should have rank 1, 2, 3. But in that case, because we cannot figure out which one is higher and lower because all same value. So in that case, instead of putting the rank 1, 2, 3, just to put them 2, 2, 2, which is the average value for all the ranks they have as 1 plus 2 plus 3 divided by 3 is equal to 2. So in that case, we don't put 2, 1, 2, 3. We just put 2, 2, 2. Okay, so it's all the rank sum should be same. Assign each rank sign with the DI is yield rank. Okay, then we have seen this one already, and we find T positive and T minus. Okay, then so we go to the table K. Table K is a specifically designed table for Wilcoxon assigned rank test. Here, as you see, n equal to 5. 5, the sample size. Okay, sample is 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, how about the 14? We go to the next page. His n is 14, 15, 16, 17, 18, blah, blah. Okay, then our table is what is this table? This is a t value. First one is a t value. Second one is a p value. So our sample size is 15, right? Here, then here So when you see the t value is increasing, then that is the probability. So cumulative probability. So as with t value is increasing, the probability also increasing. So when we have a probability 25, okay, then 0.2, actually in terms of percent, it is 2.4%. It means 2.4%. It's about 26, then 2.77%. Then when we move from 25 to 26, actually 2.5% is exceeding, okay? Exceeds to 2.7%. So somewhere between this value is 2.5, okay? But in this table, we cannot figure it out, so we pick up 2.4. Why 2.5? 2.5 is with alpha is 5%, okay? And then, so is this the alternative, the null hypothesis and testing hypothesis by the two-tailed test, okay? So the other side may be 2.5%. Okay, so there's only, so altogether is going to 5%. But as far as we have 26, okay, 26 is if we have 25, then this the probability is extreme probability is 2.4%. So is increasing here, then probability is increasing. Okay, is a cumulative probability. Our data is 34. Okay, small value is 34. When we reach 34, probability is already 7.5%. So exceeding the significance level, exceeding the 5% level. So in that case, we say this is not significant. So it is acceptable region, not extreme region. Okay, so we can say this is significant. There. So then let's look at solution process here. We have the data, we know data. Assumption is data is shooted for the Wilcoxon signed rank test format, and hypothesis is here, okay? Null is a two-tailed test. Mu is 5.05, okay? So alpha is 0.05. Then with t value, 5 value. So we are with smaller value. Then we have a table K of the appendix, okay? Then the sample size is 15, and alpha is what to remember 2.4%, but from the table. So when the value is equal to 5, okay, that is actually critical region. So in that case, T is the increase the larger number, okay, larger number is actually not significant. Smaller number is significant, okay. So the reason why I'm taking the smaller value here, larger value here, then we go the other side of distribution. But in this table, they didn't show. It doesn't mean that we don't need to have to look at both of them. So one side is enough. Okay. So looking at the one side, the other side, because it is the two-tailed test. So the easy way is to look at the smaller value. That's convenient for testing null hypothesis. Okay, so since we cannot reject a null hypothesis, so we may say population mean maybe 5 or 5. Okay, so in that case, you maybe think about why the mu is kind of a population parameter. Why does it appear in this hypothesis? That's actually we didn't calculate the mu. Just based on this mu, whether the data is located larger and smaller, something like that. So in order to be accepted, in order to accept this null hypothesis, then the minus sign and the positive sign should be equal. Okay, half of them, it means half of them is under 5.05, but half of them is over 5.05. So in the case the skewed distribution. So we can say that's enough to look at the significance level using a smaller value. Okay, the p value is going to be, okay, so already when we have the 45, the probability was 7, something like that. The same side, the other side, we have another 7.57% will be there. So we multiply by 2, then total p-value would be 0.1514. Okay, then next one is a median test. The median test is this, that a little bit different. We have urban student and rural student. Okay, so the schools located in urban and rural area. Then we have a mental score for the student. Okay, so we just want to check whether urban's mental health score and rural health score same or not. Okay, that's my question. Okay, then data is member of the random samples with 12 male students from a rural area and 16 male students from urban area. So assumption is here. The sample is an independent random sample. Second assumption is population of the same form differing only in location. So they didn't specify any population distribution, just the location, whether larger, higher or lower, then population moves to this way, that way, that's the thing. We don't care the form of the distribution. And a variable as interested continuous data. Okay. Then here the hypothesis, the testing hypothesis like that is MEM is actually median. Okay. And urban's median is equal to rural's median. That's the null hypothesis. In the alternative hypothesis, they are not same. So alpha is 0.5. Testing statistics, we have to use here. We have to calculate chi-square value here. Okay. The reason why is we have to decide according to the median. Based on median, we classify them. So okay, then we have to calculate the median here. We talk about this one later. Then, okay, let's move this one. So when this one will be a 2 by 2, I'll show you in next slide. 2 by 2 contingency table. When 2 by 2 contingency table with the degrees of freedom is 1 and the significance level is 3.841. Okay. Then based on the data, we calculate median value. Okay, we have all the 28 cases. Then in the middle of the 28 cases, 14 and 15. In terms of value, 14, 15 is the 33 and 34. So we divide by 2, is then the median would be 33.5. Based on 33.5, we classify all the cases into low value and high value into these 2 by 2 tables. So we have 28 cases, so we divide them into low and higher. Then since we are looking at we have the median, so upper median, lower median, 14 same. It should be same. But so it is a total, okay? Then there's the urban area, 6 versus 10. Here for the rural, 8 versus 4. So there's a more median, more urbans go below median, more rural goes above median. It looks like maybe some different shape, style, urban and rural. But anyway, we have to look at the significance test. But here we have 2 by 2 table. So when we are learning chi-square statistics, when you have a 2 by 2 table, then we have a calculation formula here. According to the formula, when you calculate the value, 2.33. Okay, so that's actually chi-square value for the 2 by 2 table. But our significance level is 3.841. So less than that. Then what we have to do? We cannot reject null hypothesis, right? Unable to reject. So here, when the result, the conclusion is 2 samples have been drawn from population with the equal medians. Okay, so that's the result for this test. Okay, there is a computer output here. So here, then see we have the median 1 and the median for first group, second group, median is difference. Yes, this is the table, right? 10, 6, 4, 8. So each individual for the first group, so for the first group is that median is 27, as the another group is 39.5. Okay, so the chi-square value 2.3, degrees of freedom is 1, so p-value is 0.127. So it means even though the median is like this, it looks quite different, but it's not significant. Okay, that's actually a median test. The next one is Mann-Whitney test. Mann-Whitney test is here. There's two groups. Okay, this one is, as you see in the table, the exposed group here, and then unexposed group here. So we actually studying 25 laboratory animals here, maybe 15 here, okay, 10 here, okay, 15 for exposed animal. So we formed two groups, 15 animals and 10 animals here. For the 15 animals, we put some kind of the inhalation, a prolonged inhalation of cadmium oxide. Okay, that's the exposed group. So not exposed group is this one. Okay, so what we're trying to find out is when the exposed this cadmium oxide, this toxic agent, that toxic material, then there is any difference between exposed and unexposed. Okay, that's actually our purpose of conducting this study. This is, we call it Mann-Whitney test. The two people with the last name Mann and Whitney working together and develop this test. Okay, then the data, we've seen this data already. The assumption, we assume that the assumption is a Mann-Whitney test. Mann-Whitney test of math. Okay, so here we have a null hypothesis. This one is actually one-side test. Okay, one-side test. There's the median. M is median. X is X group, exposed group. Y is not exposed to Y. Okay, so median for we just want to find out whether exposed groups the hemoglobin the value is lower because they expose themselves some toxic material. The value must be going down. Okay, so the mx is less than my. That's what we'd like to find out. Okay, we have alpha is 0.5. The test statistic. So we'll talk about test statistic in next slide. Okay, so we have 15 cases here. Then all the values are ordered in from smallest one to the largest one, and put here when they belong to X group. Then put is here. They belong to Y group is here. So when they order the value, so first this how many 7? Right, seven cases from X group, and next the 2 cases from Y group, and another 5 cases from X group. Okay, then 3 other groups is here in this way, so they are separated into X and Y. Okay, then we put the rank here, and when you give the rank, these 2 values are same, 14.2. So in that case, they should go, one must be 4, the other one must be 5. But in that case, since this value is same, so we got the order 4.5 here. Okay, then this one is also same thing. So the rank was 8 and 9. So instead of putting 8 and 9, the individual will have 8.5, 8.5 in. Okay. Then we have this another similar thing is here, rank 10.5 instead of 10 and 11. Okay, so this one here, and this here. Then now for the case group, our interest group is X, right? The exposed group. Then where the rank sum of rank is 145. You have to remember this one. Okay, this is table how to deal with the data. Let's move to the next slide. Then testers, we have a test. This is formula. T is the test statistics. Okay, Then here the S is here the sum of the rank assigned to the population X here. So the S is the sum of the ranks. Okay, ranks assigned to the sample observations from the population of X. Okay, then actually the is arbitrary. Okay, in this case it doesn't matter actually. Anyway, for the time being, so we put this one X. The total rank should be S, right? So whenever two groups the rank is same, actually in this case the point is whether ranks on both sides, X group and Y group, rank is same or not. That is the main question. Okay, so here is S. Then based on this logic, they developed this formula. Then T is in such calculated procedure, we get T value. So T value is our test statistic. Okay, then what is the distribution of test statistics? We have to go to table L, okay, for this one. Then based on this one, we have the value is a significant or not. We can determine it. You can read this one later. And let's look at then our value is like this. Okay, we have 15 sample sizes. The ranks as sum was 145. It is our test statistics here. Then the calculated value is 25. Okay, now you remember 25 here. Then if we took the two-tailed test, then we go to this one. Okay, so this why this looks like a weird. Okay, because we didn't specify the distribution. It could we don't know any about distribution, so randomly they draw this one. But anyway, point is in two-tailed test, the alpha is divided by into two. So the half of them will go here, half of them here. So whenever we have the null hypothesis of some the inequality sign, like here, it depends on situation. So here we are looking at if we have our alternative hypothesis like that, then alpha go here, and this one alpha go here. So convenient way to remember this one is it looks like arrow. Okay, so is it when you look at this one? Oh, yeah, okay. Use alpha should go this way. Okay, this one is this way. It's a more easy way to remember these things. Okay, then we go to the table for the Mann-Whitney test statistics. Here, n is actually the sample size for one group. Okay, so n is it means sample size 2. Here also it means sample size 2. Okay, so we have two groups. Okay, so each group has different sample size. So based on this one, we go to that way. So here we have 15 and 10, right? So we have 10 here, we have 15 here, but we don't have any here. So we have moved to the next slide. Okay, then we find that we 15 here. With 15 here and the 10 here. Okay, so 10, that's the X group, that's the Y group, right? Remember? Then we have this blue one here. It means blue one, and look at this one. Probabilities here. So that's a kind of certain point. When we mark 0.001, then it should be 22. The value it is actually value of t, right? T is moving to upward here, then probability is increasing. This here increasing, here increasing. So our value is 40, but when we come up to the 45, then probability 5. So the T value increasing this point, okay, then what we have to do? Unless our T value stays under 45, then if the value stays under 45, then we can say it is significant because probability is very, very low. If we exceed 45, then we cannot reject the null hypothesis. What if we change this one and this one? The same thing, okay? So I don't know whether we have this one here, 10 and 15. They change it. The location is changed, right? But this one, as you see here, this value is same. Okay, this is same. So it doesn't matter which one you look at. So based on this one statistical decision, we have n equal to 15, m equal to 10, alpha is 0.5, the value is 45. Our data, what? How much was it? 25. Less than 45. Then what we have to do? So under 45, when you say this value under 45, we have to say it is significant. Then we have to reject the null hypothesis. Okay. Conclusion: we conclude that mx is smaller than mf, my. This leads to the conclusion of the prolonged inhalation of cadmium oxide does reduce the hemoglobin levels. Okay. So that's the answer. Then what about my 25 value? What kind of probability I have? So it is from this table, it's between 22 and 30. So according to when you read this table from here, there's 0.005, 0.001. Okay. This is the computer output here. So manual U-test 25. Do you remember 25? With the 25 here, median rank sum like that. So that's the manual U-test. Also the Wilcoxon W test 145. Okay, do you remember the 145? That's the sum of the rank from the X exposed value. Okay, that's it.